Hello, in this video I'm going to explain equivalent fractions. We're going to compare two fractions and determine if they're equivalent. Now their numbers are going to be different, but what we want to do is we want to reduce each fraction to its smallest possible number and compare and then see are they the same fraction. So we can start off by doing a quick example here. So let me do a sketch real quick. So the whole represents the complete circle, right? That's the denominator. I'm going to cut this in half like this. Okay, so pretend this is exactly equal on both sides, even though it's not. And I'm going to shade one side. So here we can name this graph mathematically as part over the whole, right? We discussed this before. 2 is the equal number of total parts in this circle. 1, 2, there it is. And the 1 will represent the shaded parts. So 1 out of 2 is shaded. Let's do a similar one down here. Now pretend these circles are the same size, but rather than 2 parts, equal parts of a circle, I'm going to create 4 equal parts. Pretend each of these is an equal in size. So what I'm going to do is I'm going to shade this one and I'm going to shade this one. Now this circle is identical to this circle, and then this left half is shaded and this left half is shaded. So how do we express this figure in numerical fractional form? Well, again, we have a total of 4 equal parts. 1, 2, 3, 4, and 2 are shaded. So 2 of the 4 are shaded. Now, again, assuming these are both identical in size, so as we can see here that this part that is shaded is exactly the same area as this part that's shaded. This and this combined is equivalent to this area. So this goes to show you that, yes, these are equivalent fractions. They are the same thing. The only difference is that there are more units here. This is more chopped up into equal parts than this is. Well, 1/2 is the same as 2/4. 2/4 is the same as 1/2. The main difference is that this is a reduced fraction. Okay, this number has been reduced, and we covered that in the last video. So this is in essence what we'll be doing here. We won't be using figures to express this. We'll be using other techniques. And we covered some of those before in the previous video. All right, so let's look at the first question here. Write each fraction in lowest terms. So first we have to reduce these fractions into lowest terms. Then we'll be able to compare them more precisely rather than drawing diagrams. Then state whether the fractions are equivalent or not equivalent. All right, so what we have to do then is take each of these numbers and break them down into the prime factorization. So we have 6 over 12. Let's do that first. 6 over 12. So there's a few different ways to do this, if you recall. And one way from last video that we covered, or previous videos. So one way to do it is to say, you know what, 6 in prime number format is the same as 2 times 3. 12 is the same as 2 times 6, but 6 is the same as 2 times 3. So these are prime numbers here. These are the prime numbers for 6, the prime numbers for 12. The reason we would do such a thing is because now, since we have the same number, top and bottom, we can reduce by slashing those numbers out, which then becomes 1, because 2 divided by 2 is 1. And the same with the 3's. The 3's cancel out. All right, so we covered this last video, so I'm not going to spend a lot of time on this. So what do we have left over? Well, as we said in the last video, you can always think as anything times 1, and it's not going to change anything. So we're not going to leave this blank. We're going to put 1 here over 2. And you might have intuitively come up with that answer, right? 6 over 12 is the same as 1/2. Okay, well, let's try this technique here, or this number down here. 9 over 18. All right, so 9 is the same as 3 times 3. 18 is the same as 2 times 9. But 9 is the same as 3 times 3. Again, let's reduce. They cancel. They cancel. Times 1, right? So we don't have a blank numerator. So we have 1 over 2. So there it is. Yeah, they are equivalent fractions. They both reduce to 1/2. If we were to draw circles and filled in the circles, half of the circle, right? Half of the circle for both situations, for both numbers, would be filled in. All right, so I'm ahead of myself here, I see. So let's type in some numbers. So 612 is the same as 1/2. Let's put that in there. And we already did the work for this. 1/2. It's the same number. Now they're going to ask the question, are they equivalent? And yes, they are, because it's the same number. The same part of the fraction is filled in. Okay, is highlighted, however you want to call it. So it is equivalent. They are equivalent. Okay. Now, let me come back to that. Let me just review the other technique real quick, because it helps to know both, especially if the numbers are small. Let's do it this way. Again, you got to be good with the multiplication tables. Let's do this one first. The technique I like to use if the numbers are fairly small and certainly within the multiplication table range. What is the biggest number that you can think of that divides evenly into 6 and 12? I know 2 goes into both. It's not the biggest. I know 3 goes into both. It's not the biggest. I'm looking for the biggest number that divides evenly into 6 and 12, and that number is 6. Now you can say, okay, the number 6 that I'm thinking about divides into this 6 one time, slash the 6 out. The 6 that I'm thinking about divides into 12 two times, slash the 12, put a 2 underneath it. We don't need the thought bubble anymore. We're done with it. So what is left over? 1 over 2. Okay? And same with 9 over 18. Biggest number I can think of. Well, 3 goes into both. It's not the biggest, though. I want the biggest number to get the maximal reduction. Otherwise, I got to reduce again, which is not a big deal, actually, but the goal here is to get one shot and done, right? We want to get the biggest bang for the buck here. So the biggest number that goes into both is 9. 9 divides into 9 one time. 9 divides into 18 two times. What is left over? 1 over 2. There. See, we got the same numbers. Much quicker. Using this technique, though, you got to be really good with the multiplication facts. And actually, you should be anyway, right? With the facts, got to know the facts. No doubt about it. All right, so let's move on to the second problem here. Five over 15. Let's do this number first. So 5 is the same as 5 times 1. 5 is a prime number. We cannot break this down anymore. It's not a composite. So we can say 5 times 1. And then 15 is the same as 3 times 5. All right, now it's time to reduce. We have 5s that are the same top and bottom. And remember, they don't have to be on top of each other. As long as you have multiplication between the numbers, it doesn't matter how far down the line the numbers are, as long as the numbers are the same, top and bottom. 5 divided by 5 is 1, so this cancels out. And 1 times whatever's left over is whatever's left over. What is left over? Well, we got 1, right here, 1 over 3. That's what's left over. So 5/15 reduces to 1/3. That's the lowest terms for that number. Now we got 2/4. Now I think you know the answer to this one, right? 2 times 1, 2 times 2. The 2's cancel. 1/2. So the question is, are these equivalent? No. They're not the same number. So this is a different looking area of the circle that's filled in or highlighted. It's not the same area. It's a different looking area. All right, so, all right, let's go back and fill in what we got. We got 1/3. Let's pop that in here. We got 1/2 here. Are they equivalent? And the answer is no. Again, I'm going to review this other technique. It helps to know both. 5/15. What is the biggest number I can think of that divides into both? The biggest and only number, well, 1 divides into both. I get that sometimes from students. You can say 1. But that doesn't help you because you're back to where you started from. So don't say 1. You're right, 1 goes into both. But if 1 goes into both, that means the number cannot be reduced, right? If we have 6 over 7, and I'm trying to reduce it, and I say 1, which would be correct, it's the only number that goes into both, it doesn't help us because we're back to this. So if a number cannot be reduced, don't try to reduce it. This can be reduced. How do I know? Because I know my multiplication tables. 5 divides into 5 1 time. 5 divides into 15 3 times. Cross that out. We got 1/3 left over. And there it is, or 1/3 that we found earlier. And then we got 2/4. What number goes into both? Then you said 2. 2 goes into 2 1 time. 2 divides into 4 2 times. And here we got 1 over 2. And again, they're not equivalent. All right. I think you're getting the idea. All right, so 14 over 7. So 14 is the same as 2 times 7. 7 is the same as 1 times 7. The 7's cancel, and we have 2 over 1. Are we going to type in 2 over 1 here? No, because we're not going to do that. because this could be reduced more. Whenever you have a 1 in the denominator, don't type this in, it's going to be wrong. The real answer is 2, and the reason it's 2 is because 2 divided by 1 is 2. Okay, so this is not fully reduced. This is completely reduced. Lowest terms right here, not 2 over 1. You do not want to leave a fraction with a 1 underneath. All right, so 2. Okay, then we got 39 over 3. So 39, it's not an easy number. It's not an easy number, but I know 3 goes into both. So in other words, 3 times something, and the reason I do know that is because I'm using the divisibility rules, right? I know 2 does not divide into both. This is an odd number, so I'm going to try 3. And then 3 plus 9 is 12 using the divisibility rules. And I know for a fact 3 goes into 12. So I know that 3 times something is 39. And using long division in my head, I know the answer is 13. So 3 times 13 is 39. And then 3 times 1 is 3. The 3's cancel out, and this becomes 1. I'm left with 13 over 1, and 13 divided by 1 is 13. So 13 is the lowest terms for this number, 39 over 3. So 13. Are the fractions equivalent? Well, 2 is not equal to 13. I know that for a fact. So, no, they're not equivalent. Now, sometimes this happens. What happened here, it sometimes happens. It's pretty rare. It's pretty rare, but it sometimes happens. So when it happens, take advantage of it. And here's what I'm talking about. Remember that fractions also mean division, right? It's part over the whole, yeah, but it's also division. This divided by this. Well, wait a minute. I know that 14 divided by 7 is exactly 2. There's nothing left over. There it is. 2. I didn't have to do all that work. So just by luck, 14 is divided by 7 exactly 2 times. And also, 39 over 3. Now, this is not in the multiplication tables, right? Because it's 3 times 13, and 13 is not in the tables. So I could see how you wouldn't know this, but if you did, you would say, you know what? Wait a minute. 39 divided by 3, that's 13, right? That's 13. 3 goes into 3 one time. 3 goes into 9 3 times with nothing left over. Oh, yeah, that's 13. And there it is. So we could have done it that way too. So sometimes the top number is divided evenly by the bottom number. Just like, if it was like this, 7 divided into 14. Well, that's 2 times. Yeah, it's the same thing, right? There it is, 2. Same kind of situation. So be on the lookout for that. All right, so we got a couple more fractions here. So we have 8/12. 8 is the same as 2 times 4, but 4 is the same as 2 times 2. And by the way, you can use the factor tree that I showed before for these. Now, these are fairly small numbers, right? So that's why I'm not using the factor tree. I'm not using the factor tree only because these numbers are fairly small. So I just simply did this knowledge. I just did this right here because it's not too bad. The numbers aren't big. If this was like 81 or something like that, yeah, use the factor tree. If the number was big, use it. But if the number is fairly small, just use your multiplication facts knowledge. 12 is the same as 2 times 6, but 6 is the same as 2 times 3. So these are down to their prime factorization. Same top and bottom, cancel. Same top and bottom, cancel. And we got 2/3 left over. All right, so here we don't have to type it in, the fractions. It just simply wants to know, are they equivalent or not? So let's keep going, right? So 4/6. 4 is the same as 2 times 2. 6 is the same as 2 times 3. 2/2 cancels, and we have 2/3. Oh, wait. They're both the same number. They are equivalent fractions. Look at that. It's crazy. All right, so there they are. And again, let me use the other technique here and show you. 8/12. What's the biggest number that divides into both? 2 goes into both. It's not the biggest number. 4 goes into both, which is the biggest number, right? 8 wouldn't help us here because 8 does divide into 8, but 8 does not divide into 12 evenly. So we cannot say 8 here. 12 or 4 is the biggest number that divides into 8 and 12. 4 divides into 8 2 times. 4 divides into 12 3 times. 2/3. See that? 2/3. And then 4/6, same thing. Biggest number that divides into both, 2. 2 divides into 4 2 times. 2 divides into 6 3 times. Cross this out, 2/3. So I think this is much faster. Some students get confused with this, probably because of the lack of polishing up of the multiplication facts. That's my guess. This is much quicker. But, you know, speed isn't everything. Accuracy is important, of course. So if it means writing it out like this and using the factor tree to reduce a fraction, that's fine too. I just want to show you alternative techniques. All right, so we have one more before we switch gears, I believe, on the next problem. So I think by now you're getting the understanding, right, of what we're looking to do. 5/15, 5 times 1, 3 times 5, the 5s cancel, 1/3, 2/4. 2 times 1, 2 times 2, 2/2 cancels, 1/2. 1/3 is not the same as 1/2. So no, they're not equivalent. All right, so I think we kind of get the idea of that type of a problem. Let's keep going. So now we have a different type of fraction here. So let's write it down. 4/7 is equivalent to what over 49? So here we're looking for some number to put here that is equal to 4/9. 4/9 is equal to what over 49? That's what we're looking to do. The way we're going to do that is we're going to look at the denominators. We're going to look at the denominators. So we're going to look at this denominator right here in particular. You're going to put a multiplication dot in front, right there, multiplication dot, and you're going to ask yourself, what number times 7 is equal to 49? So we're only looking at the denominators right now. And that number is 7, you said. Correct. Now, if it takes 7, if it takes multiplying by 7 to get this to equal this, then to keep the same ratio, which means up and down, keep the same numbers up and down, even though they might be different, right? Same ratio. This is the same ratio, 1 to 2, 2 to 4, it's the same ratio because they both reduce to the same number. This reduces to 1/2, right? So you'll hear the word ratio in Math 50. I'm just throwing that out there. Heads up here. To keep the same ratio and not mess up the fraction, we have to multiply the top by the same number that we multiplied the bottom by. So this is what's in our head down here. This is what we're thinking about. We know that 7 times 7 is 49. Well, if we multiply the bottom by 7, we got to multiply the top by 7 also, because this number has to be the same so we don't mess up the ratio, 4 over 7. Okay? So then what we got to do is simply multiply. 7 times 4 is 28. That's what goes here. 28 goes here. So we looked at the denominators and we asked ourselves, what number times 7 is 49? And we said 7. Because that is 7, this has to be 7. Because this is multiplication, this has to be multiplication. Whatever you do to the bottom, you do to the top to keep the same ratio. All you got to do then to figure out what this number is to multiply 7 times 4, which is 28. And there it is. So 28 over 49 is equivalent to 4 over 7. All right? And let's go backwards real quick. Let's go backwards. We won't do this for the other problem. Let's start with this. 28 over 49. Let's go backwards just for fun, since we like fractions. All right. 28 is the same as 7 times 4. Okay? And 4 is the same as 2 times 2. You won't have to do this. I'm just trying to show you that these are equivalent and you can go backwards from here to here. 49 is the same as 7 times 7. These cancel. And what do you have left over? 4 over 7, which was our original fraction on the left. See that? So typically what happens, most of the time what happens, at least in Math 50, is that you will go from a higher fraction to a lower fraction like we've been doing, reducing a fraction. But sometimes you have to go from the reduced fraction to an equivalent bigger fraction. That's the case that you will run into when you're adding and subtracting fractions with different denominators. So get used to this. This will be one step out of 4 steps when you add and subtract fractions with different denominators. So get used to this. All right, let's go back to our problem here. So the missing block here, 28 goes there. All right, so let's erase that, and let's move on with the other ones. 2/5 is equal to what over 25? We're going to look at the denominators. I'm going to put a multiplication dot in front. I'm going to ask myself what number times 5 is 25, and I know that number is 5. If I'm multiplying the denominator by 5, I got to do the exact same thing and multiply the numerator by 5 so I can keep the same ratio. 5 over 5, 5 over 5 is 1, 1. So I'm multiplying by 1, actually. The help talks about this. So if you're confused about the help when it talks about multiplying by 1, that's what they're talking about. 5 over 5 is 1. Okay, so we don't need this fraction, but it's there. We can keep it, whatever. It doesn't really matter. The important thing here is that we're trying to find what this number is. Well, 5 times 2 is 10. And 10 over 25 reduces to 2/5. Yeah. So you can go both ways with this, right? So 10 over 25 is what we're looking for here. Once you get the hang of what the technique is, these aren't too bad. So 1 over 10 is equal to what over 40? Okay, we're going to go right here. Start right here, bottom left. What number times 10 is 40? 4. If I'm multiplying the bottom by 4, I'm going to multiply the top by 4. 4 times 1 is 4. And there it is. 4 over 40 is the same as 1 over 10. This is just a reduced version of this. Okay? So 4 over 40. So you can call this building up a fraction, right? We're building it up. We're making it bigger. We're making it bigger. And there's a reason for that. And like I said, it's for adding and subtracting fractions with different denominators. All right, so last problem here. 5 over 11 is equal to something over 55. What number times 11 is equal to 55? Well, I know 5. It's 5, right? It's 5 times 11 is equal to 55. So if I'm multiplying the bottom by 5, I got to multiply the top also by 5 to keep the same ratio. 5 times 5 is 25, and there it is. This is equivalent to this. We basically filled in the missing numerator by working with the denominator. So 25 over 55. All right, so that's how you perform equivalent fractions. So hopefully this made a little sense to you. If you like my content, click on the like button, post your comments, and subscribe to my channel. Thank you for watching.